In this question, we're asked to expand sin x over 1 minus x all squared in ascending powers of x as far as determining x to the fourth by considering the product of the expansions of sin x and 1 minus x to the minus 2. Then we need to deduce the gradient of the tangent at the origin to the curve with the equation y is equal to sin x over 1 minus x squared. Okay, let's go back to the binomial expansion. In C4, we learnt the binomial expansion. 1 plus x to the power of n gave us 1 plus nx plus n minus 1. Then we had x squared over 2 factorial. Then we had n minus 1, n minus 2. Then we had x cubed over 3 factorial, and so on and so forth. And this was valid for the modulus of x less than 1. What we can do is apply this now. So just consider first the Maclaurin expansion of sin x. We're interested in terms up to x to the fourth. So the first two terms of the Maclaurin expansion of sin x are x minus x cubed over 3 factorial. The next one is going to give me x to the fifth, and that's going to be no good. Let's now consider our expansion of 1 minus x to the minus 2. What we're going to end up with now is the following. Let's put dot 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 after that. What we're going to have now is 1 plus 2x, then we're going to have plus, and we'll have now n, which is going to be minus 2, n minus 1, which is minus 3, then we can have minus x squared over 2 factorial, then we'll have plus, and we'll have minus 2, and then we'll have minus 3, minus 4, and then minus x cubed over 3 factorial. Let's consider any more values in this. We need to go up to x to the fourth. The smallest value that I'm going to get now is going to be, if I expand this out, I'm going to get, if I take any more terms on this, the lowest I'm going to get by expanding that is x to the fifth, which is not what I want. So this now is what we want to use. So we'll say 1 minus x now to the minus 2 is going to be giving us 1 plus 2x. We're going to get a positive on this one. The 2's going to cancel, leaving us plus 3x squared. On this one, 3 factorial is 6, which will cancel off with those. All of these are negatives, so that's going to give us a positive, and we'll end up with 4x cubed, dot, 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 and so on and so forth. So that's the expansion right there. So all we're interested in now are finding terms up to and including that in x to the fourth. So we're going to multiply these. So multiplying sin x by 1 minus x to the minus 2 will give me x minus x cubed over 3 factorial. 3 factorial is 6. And we'll multiply that by 1 plus 2x plus 3x squared plus 4x cubed. So expanding this out, what we can say then is that the value of sin x over 1 minus x squared is going to be approximately equal to, we can have x, then we can have plus 2x squared plus 3x cubed plus 4x to the fourth. Then expanding out here, the negative x cubed over 6, that's going to give me now negative x cubed over 6. Expanding the next term out, I'm going to get now negative, what's that going to give me, 2 over 6, so it'll be negative 1 over 3 x to the fourth, or 2 over 6. So from here we can do a bit of tidying up, and we can state now that sin x over 1 minus x squared will be equal to x plus 2x squared. Now we've got here, if I've got 3x cubed minus 1/6, so if I switch these into 18ths, that's going to give me, what's that going to, so if I switch it into 6's, it's going to give me 18. So we can have plus 17 over 6, isn't it? If I switch those into 6's, I've got 18. 17 over 6x cubed. Switching those up into thirds, that's going to give me 12 minus 1, which is going to be plus 11 over 3x to the fourth, and so on and so forth. So that's our expansion right there, okay? And we've done that. So nice and, well, say straightforward, fairly logical. Okay, next part, what do we need to do on the next part? We need to deduce the gradient of tangent at the origin to the curve. So what we want then is the derivative. So remember, they're stating that this is y, so we're saying y is equal to this. So dy by dx, the derivative, is simply going to give us 1 plus 4x, and then what's that going to give us? Plus 17 over 2, and that's going to be 17 over 2x. 17 over 2x squared. Now anything else beyond that, all we're doing now is taking higher derivatives, and consider that we are looking at x is equal to 0 to evaluate our gradient. So all of these terms are just going to be 0. So we end up now deducing that dy by dx is simply going to be 1, because if I've got an x, I've got an x. I'm always going to have x's from that point on. The gradient at the origin is going to be 1. So gradient at origin is equal to 1, and you can do something along those lines, show that you're differentiating it, and show that all of these higher terms, you might even want all higher terms, will differentiate to include an x of some power. Therefore the gradient at the origin is going to be 1.